We have a question here that says, a spaceship with a clock displayed on its side is stationary relative to your frame of reference, or your reference frame. You observe the clock be running at the same rate while it is stationary. Later, the spaceship is traveling at 0.8 c relative to you. How much time will pass on your watch as 80 seconds passes on the clock attached to the ship? Now the question may sound a bit confusing, but it's simply a time dilation problem, because we're talking about two reference frames, one being stationary, which is your reference frame, and then another reference frame of a spaceship moving at 0.8 c, or 0.8 times the speed of light, or 80% the speed of light. And then you're talking about how much time will pass on your watch if 80 seconds passes on the clock attached to the ship. So we have a clock that's moving, and that clock that's moving is recording 80 seconds. So during that 80 seconds, what would you record if you were stationary and not moving at 0.8 c? Now, the first thing you normally do with these questions is you just draw a diagram to try and get your head around it a little bit. And that's what we'll do. So you have your reference frame. We might say, reference frame of Earth. I would say reference frame of E for Earth. And according to you are stationary. You have a rocket, which is traveling to the right at velocity, which equals to 0.8 c, or 80% the speed of light. And in their reference frame, let's see, we'll call that reference frame R for rocket. And their reference frame, their T prime, their delta T prime is going to equal to 80 seconds. So in their reference frame, 80 seconds passes, but in your reference frame, that's what you want to work out, how much passes in your reference frame. So that's what it's asking. So simply, it's a time dilation problem. So we work out we use that time dilation formula, which we derived in an earlier video, which simply says our delta t is equal to our proper time divided by our 1 minus v over c squared. Now, which one will record our proper time and which one will record out simply our delta t value? Well, we could use a definition of proper time, but we could simply look at, from your point of view, you are stationary and they are traveling at a certain speed. Because they're traveling at a certain speed, they're going to measure a shorter amount of time than you. So that is that, their delta t prime is going to be less than your delta t. By the rules of time dilation, someone that's moving at some velocity, their time frame is going to be less than your time frame, and so that's going to hold up. Or simply, in this formula, we have our proper time, or our delta t. Our proper, let's see, this value here, because we got our proper time divided by a number which is less than 1 usually. Because we're dividing by a number less than 1, it's like multiplying by a number that's greater than 1. And so our delta t is going to be greater than our proper time. So because our little delta t is going to be greater than our proper time, therefore, in this case, our delta t prime must be our proper time, this. So if this equals this one, this one's going to equal this one. So this delta t is the time frame according to the spaceship. While this delta t is going to be, your reference frame, will say Earth. So we know that the value that it's recorded on Earth, our delta t, must be greater than the time recorded on the spaceship, and so we should get a value which agrees with that. If we didn't get a value, if say, that the time that was recorded on Earth was less than the time recorded on the rocket, then there's something wrong with what you've done. But you should know if someone is stationary, and you compare their time compared with someone who's moving, but the people are moving, their time frame is going to be less, or they are going to record a less time for event than you. You might record an hour for event, they might record like half an hour if they're moving at a certain velocity. So I hope I didn't confuse you there. Our spaceship is recording our proper time, our Earth is recording our delta t, and we can simply plug those values into this formula here. We're trying to work out this value here, so it's already in the form that we want it in. So we simply say our delta t is equal to our proper time. Well, our proper time is 80 seconds divided by our 1 minus, well, what's the velocity? The velocity is 0.8 c divided by c, and that's going to be squared. You've got c over c, so c's cancel, and we're simply left with 80 seconds divided by, what do we have? We have 0.8 squared, so we can work that out. We say 0.8 squared is 0.64. We're going to be take 1 minus 0.64. It's going to equal to 0.36. Then we're simply taking the square root of that value here, which is going to be 0.6. So it's going to be 80 divided by 0.6, which is going to equal to 133.3 seconds. And that's going to be equal to our delta t, or the time recorded from the Earth's point of view. So that's simply our answer. We get a time frame which is greater than the time frame that was recorded on the ship, because the Earth is stationary relative to the, we're saying the Earth is stationary, rather and the ship is traveling at 0.8 c. So in this case, what is 80 seconds on the ship is 133.3 seconds on Earth. So in effect, if someone's on the ship, they would have aged 80 seconds. Well, if someone's on the Earth, they would have aged 133.3 seconds. So if someone that's on the Earth is going to age faster than someone who's on the spaceship. And the ratio of how much they age compared to the person on the spaceship is going to be relative to the velocity of which the spaceship is traveling at. So that's the answer there, just simply 133.3 seconds, and we see another consequence of time dilation, where the time for one frame of reference is not equal the time of the other frame of reference.